So if you're looking through the PowerPoint, you'll see some structures there. But again, it's missing a lot of the rules that we need to learn, some tables that we need to look at, some figures that we need to use to understand what's going on with Lewis symbols and structures, resonance, and how we calculate formal charge. And I just don't feel that it's there in the PowerPoint. So we have an example of what we see for Lewis dot structures. So you've seen me draw these before. So if I take sodium here, this is a sodium atom. So this describes a sodium atom. Okay? This is what we consider our Lewis structure for sodium. So we see that symbol here, sodium, magnesium, however many valence electrons they have, and we can determine that by what group number that they're in. Right? So magnesium has 2 valence electrons because it's in group 2. Aluminum has 3 valence electrons because it's in group 3. And we write out that Lewis dot structure. So here, let me get rid of this one. This marker is about to die. Would this be correct? Yeah, absolutely, because it's not mandatory that we put this electron up at the very top. If I drew it like this would still be an acceptable drawing. If I drew it like this, it's still an acceptable Lewis structure, right? It does have its 3 valence electrons, and we can see that. So, in understanding these electrons between what we consider a Lewis dot structure for a calcium atom and then what we consider to be the cation for that. So here is our Lewis dot structure for this. And if we give this a charge and give it a 3+ charge because it's going to lose these 3 electrons, is that we would have this here. But this has to do with, we consider the law of conservation of mass, right? Law of conservation of energy, right? Is that these 3 electrons simply can't just disappear, right? Can't just vanish. They did go somewhere. So we want to make sure that this is balanced. If I have aluminum atomic number 13, if I start with 13 protons and I start with 13 electrons, I still have to have, even when it becomes a cation, I still have to have 13 protons and 13 electrons. Right? So we can't just have this stuff disappear. They do get shuffled around, but we still have to know that those electrons are there. And that's what these are representing. So here we have a sulfur atom. If we add 2 electrons, then we get its anion. So it is just the reverse of what we're seeing there. So when we draw ionic compounds, Lewis structures for ionic compounds, we want to enclose the anion in some brackets that we see here, right? So here's our sodium atom. We're going to transfer this 1 electron to chlorine. It's going to take on that negative charge here. So for a Lewis structure, we put the charges here and we enclose that anion in some brackets. So here we have our 2 elements, and then we're going to put aluminum here. It's going to gain these 3 electrons, so we're going to have nitrogen. We're going to enclose these in brackets, and then we would put, not out here, we're going to put, they want it on the outside? All right. So 3 minus, and this is 3 plus over here. So we're looking at this for the Lewis structure of an ionic compound, right? Ionic compounds are some metal to non-metal bond, right? This is a metal, non-metal, and we have some ionic bond between those. So we can see just different examples here. If we do happen to have more than one, we're just going to put that subscript on the outside of that. So let's take aluminum again. Here's aluminum. This time we're just going to add, how about we add chlorine to this? We need 3 of these here, so let's put a 3 in front of here for 3 of those. And then we have aluminum, which is 3+, chlorine, all of its valence electrons. There's going to be 3 of those, and then we have the minus charge on the outside, right? Notice that I didn't put 2 minus or 3 minus, right? I just put 1 minus because I know that there's 3 of them there, okay? The charge that we put up here is not the overall charge. We do that math in our head. -1 times 3 is -3. Okay, cancels this out, okay? But again, these are examples of Lewis dot structures for ionic compounds. So if I did this, is this the Lewis dot structure for an ionic? No, because there's nothing around here. We need to put those 3+. And again, this completes our Lewis dot structure for an ionic compound. So Lewis dot structures get more complex for covalent bonded molecules. Molecular compounds such as this, because they end up sharing. So we need to understand how to draw. There's rules for drawing Lewis structures for covalent bonded molecules. So we'll go with this example here. 4, 5, 6, 7. This is chlorine. Chlorine here, 1, 2, 7. Covalently bonded molecules share their electrons. And as a reminder, everything but, let's put hydrogen and helium, we're looking for the duet rule. And everything else, we're looking for the octet rule, right? This is our 8 electron rule. So currently this only has 7 because it's in group 7. This has 7 because it's in group 7. And they're going to share these together. So we end up putting those here. So now that they're sharing these together, chlorine can include this into their octet, and this chlorine can include one of the electrons into their octet. So they both have 8 valence electrons. And we can draw it like this, but since these 2 electrons are making a bond, we're going to signify this as our bond. This represents 2 electrons here. So if we count these electrons, 2, 4, 6, 8, 10, 12, 14, 2, 4, 6, 8, 10, 12, 14. So these lines here are going to represent 2 electrons that are creating a bond between those. So our octet rule. Right, carbon tetrachloride here. So we don't want to draw all of these valence electrons. These 2 are obviously making a bond, so we put a line. These 2 are making a bond, so we put a line, so on, so on. And we put a line here. We see that with silane as well. Is that when we have those 2 electrons making a bond, that we're just going to convert that into some straight line. So anytime you see a straight line, that represents some bond here. So if we're looking at these, we can verify that it has 8 valence electrons. So hydrogen, or nitrogen here, 2, 4, 6, 8. Nitrogen has 8 valence electrons. It's filled its octet. And hydrogen, the rule for that is the duet rule, which is just 2 electrons. And here it is. We can see the other examples as well, water, hydrofluoride, 2, 4, 6, 8, 2, 4, 6, 8. They all contain their 8 valence electrons. How we describe some of these valence electrons is that the electrons that are sitting here, these are what we're going to consider a bonded pair of electrons because they're in a bond. These are what we call lone pair. These are lone pair of electrons. So this is a bonded pair, this is a lone pair of electrons, and this here is an unpaired electron. So when we're describing these electrons, these valence electrons, right? When I say a bonded pair, I'm talking about the pair of electrons that are in the bond. A lone pair is just a set of electrons that aren't bonded to anything. And then this is an unpaired electron. So we have different ways to describe these electrons as we see them. Now, what we see in this figure here is these are what we call single bonds. So here, there's one bond between hydrogen and fluorine, or oxygen and hydrogen, and then we have what's considered to be double and triple bonds. So for a double bond, we count this is 2 electrons, this is 2 electrons, so there's 4 electrons between this carbon atom and this oxygen atom. And for a triple bond, we would see, let's say, these are all for double bonds here. For triple bonds, we're going to see 6. So there are 6 electrons between carbon and oxygen here, and we use those 3 lines. So we understand those electrons and this octet rule. It's not carbon it's not hydrogen or helium. So we need to fill the octet rule. Because they're sharing electrons, all of these electrons here, 2, 4, 6 electrons here, are being shared between carbon and oxygen. So if we're counting carbon's octet, its electrons, we can say 2, 4, 6, 8. For oxygen, 2, 4, 6, 8. Because they're sharing these ones in the middle. So each one of these have filled their octet rule. Since they are sharing them, we can do this with, let's see, carbon dioxide. Because they're sharing these 4 in the middle, these 4 electrons are shared to oxygen, these 4 electrons are shared to carbon. We can count them in each other's octet. So for oxygen, 2, 4, 6, 8, carbon, 2, 4, 6, 8, oxygen, 2, 4, 6, 8, and each one of these atoms contains 8 electrons for their octet rule. So there's rules in determining how we put and how we draw these out. So let's begin with, let's say carbon dioxide. Or maybe we should start with carbon monoxide. Now, carbon dioxide. So if we wanted to draw the Lewis structure for carbon dioxide, the first thing we do before we start drawing anything, we need to know how many valence electrons that we're working with. And we don't want to go above those electrons, and we don't want to miss any of those electrons. We need to have all those valence electrons in the Lewis structure. So for carbon, carbon is in group 4. So how many valence electrons? 4. And oxygen is in group 6, so it has 6 valence electrons. The charge is -2, but for valence electrons, it does have 6. But there's 2 of them, so that's going to be 12. So 4 plus 12 electrons, so there are 16 valence electrons that have to go into this structure. So this is step 1 right here, is figure out how many valence electrons you have to work with. The next is we're just going to build a bare bones structure of CO2. So we can do this, or we can do this, but only one of these is correct. The way that we determine which element goes in the middle is the one that's the least electronegative. Right? Carbon is less electronegative than oxygen is. So we're going to put that one in the middle. So we're not going to be using this one here. So this is step 2. So step 2 is to just draw a bare bone structure and determine which element goes in the middle. Then the next one is we're going to fill, this is 2, 4. So out of the 16 electrons, we've only used 4. So there are 12 electrons left. We're going to fill the terminal atoms up because we want to get this octet rule for the terminal electrons. So we're going to put, there's 2, 4, 6, 8. So the terminal ones now have their octet rule filled. 2, 4, 6, 8, 2, 4, oh, we needed 12, 2, 4, 6, 2, 4, 6, okay. 16 electrons, I want to just make sure we're on track here. 2, 4, 6, 8, 2, 4, 6, 8, so we do have 16 valence electrons, yes.
Why does oxygen take carbon's electrons?
Well, it's not taking them just yet, is that we're building a Lewis dot structure. So there's steps in order to do that. So step 1 is determine the valence electrons. Step 2, build a bare bones structure. The next is we're going to take the remaining electrons that we haven't used and put them on the ends of those atoms. So this is step 3 now. Has oxygen filled its octet? Has carbon filled its octet? No. So this is where we start bringing in, we know that oxygen has to share some of those electrons. So if we take these 2 electrons here and we share them, does oxygen still have its 8 valence electrons? Yeah, it's 2, 4, 6, 8. Does carbon have 8 just yet? Not yet, but it does have 6. We're getting closer. So we're going to take these 2 electrons and we are going to share those with carbon. So we start bringing them in to fill this octet up. So we start sharing bonds. So now if we clean this up, we're going to put 2 bonds between these carbons and oxygens, and then we'll just kind of straighten this out a little bit. So there's multiple steps in order to. So does that kind of help out now? It's not necessarily taking all of them. It's that we just haven't decided which ones we're going to share just yet. So those are rules that we have in order to determine what those are going to look like. So we have some examples here that we can go over. Some easier than others. So here we have, let's see here, is that 4? Is that what they give us? Yes. Silicon, 4 valence electrons. Hydrogen has 1 valence electron, but there's 4 here. So there's 4 electrons here, so we have a total of 8 valence electrons that we have to deal with. Let's draw a bare bones structure. We're going to put silicon in the middle, and then we're going to put hydrogen here, hydrogen here, hydrogen here, hydrogen here. And let's see if we have any electrons left. There's 2, 4, 6, 8. We've used them all up. Did hydrogen fill its rule? Yes, Brandon says yes, but Sue says that it doesn't, so let's make sure we're clear on this. How many electrons does hydrogen require? Just 2. This is a duet rule. Did silicon fulfill its octet rule? Yeah, 2, 4, 6, 8. So silicon has 8, hydrogen has 2. This is our Lewis structure for silane. We do have some negative charge up here. When we have a negative charge, that means we have an additional what? Electron. So that has to be included into this. So we have carbon, hydrogen, oxygen. Carbon has 4 valence electrons. Oh, that's a horrible looking 4. 4 valence electrons. Hydrogen has 1 valence electron. Oxygen has 6 valence electrons. And then we have this charge here. This negative charge is also going to bring an additional valence electron. So we have a total of 12 valence electrons. So here, we need the least electronegative element to be the central atom. So hydrogen and carbon, this is where we need to have some understanding between carbon and hydrogen. The further away we get, the less electronegative we are, which means that hydrogen is less electronegative than carbon. If we did this, then we would have to add carbon, oxygen, and oxygen. But what's wrong with this picture? Hydrogen has how many valence electrons? Has too many. It can only have 4. I'm sorry, it can only have 2. Big mistake there. It can only have 2, but we've given it 6. Hydrogen will never be the central atom. So we can always skip that one as far as being the central atom. So now we have to determine between carbon and oxygen. Carbon is less electronegative than oxygen, so carbon is going to be our central atom. We're going to attach hydrogen to it, and we're also going to attach oxygen to it. Does it matter whether it's up here or over here? No, absolutely not. 12 valence electrons, we've only used 4. 5, 6, 7, 8, 9, 10. So now, there's 2 that we have not used just yet. If you run out, because the hydrogen has its 2, oxygen has its 8, anything left over, just give them to the central atom. Okay? Anything left over after you've given all of the other electrons away and filled out the terminal atoms, they have their octet, just give the rest of them to the central atom. Octet rule. Is oxygen good? Is carbon good? Yeah. How many does carbon have? 6. Is it good? No, we need 8. You had a question, Dave.
I'm not sure if it was intentional, but there was 2 oxygen atoms.
Oh, we can fix that. We can fix that. There is 2. Let's go with this one first. Yes. We'll do CHO2 next. Okay. So here, we know that carbon does need more. So oxygen has a lone pair here that it can share. So if we bring these over here, Did octet fill its rule? Yeah. Hydrogen look good? Carbon, does that look okay? Yeah. 2, 4, 6, 8. Is that this is the Lewis dot structure. Now it did make, so let's correct this. So we had C, H, there's O2, and then we had the negative charge here. So we have 4, this is 1, this is going to be 16, nope, 12. And then we have an additional one here. So we have 16, 17, 18 valence electrons. So we build our bare bone structure. Here's carbon, hydrogen, oxygen, and oxygen. What's the next step here? What was it? Yeah, on the out. Yeah, we want to put electrons out here. So we've used 2, 4, 6 of these. So we have 12 electrons left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm out of electrons, so I'm not going to put anything here on carbon. Is this oxygen good? Yeah, this oxygen's good. This hydrogen's good. Is carbon good? No. Carbon needs how many more electrons? 2. Well, we can borrow some, we can share some with either oxygen. It doesn't really matter. Is that we can take these two and put them here. Is carbon good now? Right? Everything has its octet structure. Now, the next topic here, because this is one structure. We have this term that we call resonance. Is that this is not the only way that we can see it. Is that we could also draw it this way. This is also an acceptable structure. These are what we call resonance structures. Oh, actually, there we go. Too many arrows there. These are what we consider resonance structures. Okay? Is that they look different here simply because these electrons jump from one end to the other. So it can be written this way, it could be written this way. So these are what we consider to be resonance structures. There's additional work with resonance structures that we do have to consider. Let's see, let's work on just a couple more Lewis structures. NO plus, so NO plus. So NO plus, so nitrogen has 5 valence electrons and oxygen has 6 valence electrons. But the plus sign means that we have to remove one of these valence electrons. So in total, we have 11 valence electrons, but because of this, we only have 10 valence electrons to work with. So if we see that plus sign, we have to remove one of the overall valence electrons. We draw our bare bone structure. And we've only used 2, so we need 8 more electrons to use. So we're going to say 1, 2, 3, 4, 5, 6, 7, and 8. Well, oxygen looks good, but nitrogen's missing 4 electrons. That's fine because oxygen can share. We're going to take these here, and we will now share them. Oxygen 2, 4, 6, 8, we're still good. Nitrogen 2, 4, 6, not enough. Let's take these electrons and we'll share those. Oxygen is now 2, 4, 6, 8. Nitrogen is 2, 4, 6, 8. So each one of those have now met their octet rule. Oh, let's see here. let's do one with multiple carbons. How about none of those? How about C2H2? Let's work on this one. So C2H2, carbon, there's 2 of them, has 4 valence electrons. So carbon has 8 valence electrons, and hydrogen here, we're at 2 valence electrons. So a total of 10 valence electrons for this structure. So step 1 is done. Step 2, we're going to put together this bare bone structure. So carbon, hydrogen. Well, I know that hydrogen can't be in the middle, so let's put the other carbon here, and we'll put the other hydrogen here. Now, there's probably several structures we could make. How do we know that it's not this, this, and this? Right? So we're just going to take a look at a couple different structures here. We've used 2, 4, 6, but there's 10. So we're going to add some more electrons here, and then we'll put it over here. Hydrogen has 2, hydrogen has 2. This carbon has 2, 4, 6, 8. This carbon has only 4. So we have to share electrons. So let's take these electrons and share them. 2, 4, 6, 8, 2, 4, 6, not enough. So we're going to take these electrons, share them, and now we've fulfilled this octet rule. Here, 2, 4, 6, 8, nope, that's not the end. 2, 4, 6, 8, 10. Well, this carbon doesn't have enough. This carbon has too many. So we're going to take these and we are going to share them. Carbon 2, 4, 6, 8, right? Carbon 2, 4, 6, 8. So this structure is also possible. But which one is correct? How we determine the correct one is by something that we call formal charge. We'll take a look at those here. We'll come back to this, but there's something that we call formal charge. So each one of these atoms have what we consider a formal charge. The formal charge is a calculation that you need to make. To calculate formal charge, you're going to take the number of valence electrons, and you're going to subtract the number of lone pair electrons minus half of the bonded electrons. So to figure out formal charge, and we have to figure out the formal charge of each atom. So we're going to take the number of valence electrons, subtract the number of lone pairs, and half of the bonded electrons. So if we want the formal charge for hydrogen, how many valence electrons does hydrogen have? 1. And 1 minus how many lone pairs does hydrogen have? 0. Minus half of the bonded electrons. So there's 2 electrons in here, half of those is 1. So the formal charge on this hydrogen is 0. If this hydrogen is 0, should we recalculate this, or do we think this is also just 0?
Also
That's also just 0. It's hydrogen 1 bond, that this is also simply just going to be 0. Now between these carbons here, let's determine the formal charge on this carbon first. So this carbon right here, how many valence electrons does it have? 4. Minus, how many lone pairs does it have? 0. How many bonded electrons do we see here? 2, 4, 6, 8. And we need half of those. Minus 4 is equal to 0. So the formal charge on carbon is 0. Now let's take a look at this one up here. 4 minus how many lone pair electrons?
2.
2. 4. There's two lone pairs, but we need the number of lone pair electrons. 2, 4. Minus half of the bonded ones. So there's 4 in the bond. We're going to subtract just 2 of those. And what is the formal charge on this carbon? Minus 2. Well, now let's compare that to this one. Should we calculate hydrogen? It has 1 bond. Do we need to recalculate it, or do we know it?
No.
We know. It's just going to be 0. So this is going to be 0. This is going to be 0. This carbon, 4, minus how many lone pairs? 0. Minus how many? And at this point, it's half of the bonded ones, but you can just count up the number of bonds that it has, honestly, right? So carbon has how many bonds?
4.
4. So what is the formal charge on this? It is 0. Which means what's the formal charge on this? It's also 0. With this negative 2 charge, and this being 0, 0, 0, which one is more stable, do you think? This top one is. So this would be the correct Lewis structure. Is this possible? In theory, it's possible, but this one is definitely the more stable structure, and this would be the correct answer here, because we know what those formal charges are, and we always want the one with the lowest formal charge. We do have elements that have odd electrons that don't have a way to balance out. Sometimes we have a charge, we can add an electron, or we can remove an electron. We have an even number of electrons to deal with. But sometimes we have odd electron molecules where this octet rule 2, 4, 6, 8, octet rule 2, 4, 5. And even if we did share, if we move one of those electrons there, is that this still hasn't fulfilled its octet rule. These do exist. These are what we call radicals, right? And these radicals are quick to react with something because of this solely unpaired electron here. So that can happen. And then we have what we consider electron deficient atoms, such as boron. Boron, aluminum, beryllium is another one. Yeah, beryllium is another one because it has its elements in the 2s. There's no electrons in the 2p subshell. Is that we only have electrons in the 2s subshell. So beryllium is content with just 4. 1s2, 2s2. Beryllium is content with just having 4 electrons versus having 8 electrons. So there are exceptions to the rule of that octet rule. Boron is another exception. Boron is completely happy with just those 6 valence electrons. It doesn't require to have 8. So there are going to be some exceptions to the rule. So just kind of know those exceptions, you know. Hydrogen, helium, beryllium, lithium, aluminum, boron. Then we have what's considered hypervalent atoms. sulfur has how many sulfur has how many electrons here, right? If we're looking for the octet rule, 8 electrons, 2, 4, 6, 8, 12, 2, 4, 6, 8, 10, 12. So 8 versus 12 electrons. These are what we call hypervalent. Sulfur for sulfur, the reason we can put 12 into sulfur is because sulfur has access to the d subshell. So given enough electrons around sulfur, there's room to put those electrons elsewhere, which would be the 3d subshell. When we're looking at these, at the periodic table, anything here and here, you cannot go over 8 electrons because there is no 2d subshell, right? So the number of electrons for neon, fluorine, oxygen, all of these are going to be a maximum of 8 electrons around it to fill its octet rule. But beyond that, phosphorus, bromine, thallium, xenon, they have access to that 3d subshell. So it can take some additional electrons into there, right? So we can actually fill these other elements with some other valence electrons to get those to bond. So so we just need to be aware of that. If you have too many, because remember one of the steps is any electrons that are left over, we're just going to stick them onto the central atom. And if it goes beyond 8, there's a reason. As long as it is in that third energy level, right, we're good. We can put those elements there because those are what we consider to be hypervalent molecules. Right? Another example, right? Xenon is way down here, but it's hypervalent because it has access to a d subshell. So 2, 4, 6, 8, 10, 12, and we can have those because it does have access to those other, to that d subshell. So calculating formal charge. So let's get back and make sure we're understanding to calculate the formal charge here. So let's calculate the formal charge of so the formal charge of the chlorine here, chlorine has how many valence electrons? Rhymes with Evan. 7, perfect, yeah, so 7 valence electrons minus the number of lone pair electrons. So how many lone pair electrons are there? 6 minus how many bonds?
1.
This equals 0. So this is 0. This is 0. So all of the chlorines here are essentially identical, so they will all be 0. For iodine, how many valence electrons for iodine?
8.
Also rhymes with Evan.
7.
7. Perfect. So 7. And how many valence electrons does it have? or I'm sorry, how many lone pair electrons?
4.
4. And minus the number of charges. Oh, I'm sorry, bonds. We have 4, or half of the bonded electrons, which is going to be 4. So this is going to equal -1. And it matches here that here is our -1 charge for this particular element, right? Is that we're starting to understand reasons why these charges exist. Is because of that formal charge that we see. Does anybody recall the charge on phosphate? Yes.
You said half the bonded electrons?
Half the bonded electrons. So how many bonded electrons do we have here? There's 8, and we need half of those. So this is, but normally, just a quick and dirty method to do this is just count the number of bonds up. It's 1, 2, 3, 4. Okay. Does anybody recall the charge on phosphate?
-3.
-3. So let's why is it -3? Let's take a look. Phosphorus is in group 5, 5 valence electrons. Oxygen is in group 6, 6 valence electrons, but there's 4 of them there. So how many valence electrons do we have? 24. There's a 3- charge here. So I have to add how many additional electrons? 3. So this totals up to 32 electrons. We're going to put phosphorus in the middle because it's the least electronegative. We've used 8 out of the 32 electrons, which means we have 24 electrons left. Filled its octet rule? Yeah. Filled its octet rule? Yeah. So all of these fill its octet rule. But here, phosphorus is in 3s2, 3p3. It does have access to this additional, the D subshell here. So if we determine what the formal charge is here, let's determine these formal charges here. So here we have a formal charge of, let's see, 6 valence electrons minus 6 lone pair electrons minus half the bonded electrons is equal to -1. So the formal charge here is -1, this is -1, this is -1, this is -1. And let's figure out what it is for phosphorus. Phosphorus is 5 minus 0 minus 4 is equal to +1. That does come out to 3-. Well, let's look at some resonance structures. If we do this, this is -1, this is -1, this is -1. Nope, I'm sorry. This is -1. But let's now do the formal charge on oxygen. So this oxygen, 6 minus 4 minus 2 is 0. This is going to be, for phosphorus, it's 5 minus 0 minus 5. This is also 0. Which one is more stable? Yeah, this one over here is more stable than this one over here. Can oxygen or can phosphorus have this many? Phosphorus has 2, 4, 6, 8, 10.
Yes.
Because it's hypervalent. We can add more to phosphorus. So here, this is now 0, this is now 0, this is 0, this is 1 minus, this is, oh no, this is not, this is minus 1. So here, which one is more, comparing this, so this is also 3 minus, this is 1, 2, this is also 3 minus, right? But which one is more stable, right? Because both of these are neutral here, but this has a negative charge. These have 0 formal charge here. So there is a deciding factor for which one of these two, even though we have 2 atoms with 0. For this, we need the periodic table. According to periodic table trends, right, fluorine is the most electronegative. And if we go away from that, they tend to be less electronegative. Right? Between oxygen and phosphorus, which one is less electronegative? Phosphorus. So between phosphorus and oxygen, oxygen should have a partially negative charge, and phosphorus should have a partial positive charge. Do you think that it's okay for phosphorus to have a negative charge if it should be partially positive, not stable at all? Is that here, this could be partially positive, right? So it's neutral right now, there's no formal charge on there, but it could be, it's okay to be partially negative. So that would be the deciding factor there, is we don't want to have the least electronegative element to have a negative formal charge.
Should all hypervalent molecules have partial positive charge? Like with their central atom charge?
They can, like it would be okay if this, see how this is +1 over here? This is the least electronegative element between phosphorus and oxygen. So it's okay to have a +1 here, right? If we had to rank the stability of these, this is the most stable because there's 2 formal charges here that are 0. And phosphorus is not negative and oxygen is not positive, right? That we wouldn't want that. Here, a little less stable because there are no, everything here has a formal charge. But this one, no, this one is not going to work because we don't want this phosphorus here that is the least electronegative to have this negative formal charge. Okay? So we do want to consider formal charges each time you are drawing any Lewis structures, is we always want to have that. So here we have some other structures here, they're all resonance structures. Nitrogen, sulfur, carbon. So if we put these together here, we can see that nitrogen is negative over here, and then we have carbon, oxygen. We have these formal charges here, we have these formal charges here, but we can see that the most stable structure we're going to see is this one here, simply because there's no formal charge on carbon or sulfur. We get a little less stable here, and then we get completely unstable here. But they're all different resonance structures for that. So using formal charge to determine what those structures are. And resonance structures, right? So we do have examples of resonance structures here. This goes beyond just flipping it this way. It's not that we moved it around, okay? Is that these electrons here moved, okay? So these electrons here end up moving down here, crossover. So they are resonance structures, and those electrons do actually move. And so I think we're, enough time for the last chapter here. We'll be talking about bond length and shapes. So I think we have a pretty good understanding of drawing these Lewis structures. But these Lewis structures do take on shapes. So all of these atoms that or these drawings we have here, is that if we had to draw this one here, is that this would not be the correct structure. Right? It is a drawing, but it's not correct, is that this is a more accurate depiction of what we see here. See, we have this would be bent down a little bit, this would be bent down a little bit here. What causes this to happen? Why is it this and not this? So what happens here is these electrons here create a cloud of electron density, a cloud of negative charge. Okay? And here we have this big negative charge here, we have this other negative charge here. Actually, I should make it a little bit longer. Let's go like this, more understandable. This is a cloud of negative charge here that it's displaying. And don't forget that there's electrons in here. And what happens when you put two negative charges together? They repel. They don't want to be. So these electrons here don't want to be anywhere near this negative charge. So in order to offset that, that's why that's why we have what we call bond angles. This bond tends to move and repel so that here, that we can see that we're just kind of a maximum distance away from each other. Right? Because these are going to create the electrons here create some electron density, and that we can see here that all of these are repelling each other. So this is why we understand it to not be this, right? Even though this one is repelling, we don't want to put it down here. Right? Because this gap is too big here. These two here don't want to be next to each other. So we have this kind of evenly laid out response to that. So this is what we call Vesper theory. I know it's V-S-E-P-R. It's not Vesper. It is Vesper theory. So Vesper theory helps us understand what these bond angles are and how they're repelling each other. So when we have this is what we call a linear structure. It's very straight. So this linear structure here, is that these elements are identical here, and there is a 180-degree separation between the both of those. So we end up calling this structure linear, that they're the maximum distance away. Now, if we take a look at this is beryllium. It does not require 8 valence electrons. It's okay with just 4 because it's happy in that 2s subshell over there. So there's no electrons to offset this. Even though there's 3 elements here, it is 180 degrees. Here, this also has 2 elements. But the difference between H2O and BeF2, right, beryllium fluoride and water, is these electrons here. What do you think would happen? What's the response to these here? Is that they are going to repel these here. So for water, we see these bond angles here occurring because of these here. So now that we have this density over here, right, it's not interfering with this density is not interfering with this one, and they're all the maximum distance that they can be with each other. So when we have two regions of high electron density, right, this was the linear structure that we see there. Right? When we have three, we're gonna need to memorize these bond angles, but I have there's a different table in the book that I prefer other than these. This is just kind of what helps us understand what's going on here, and these clouds of electron density. So between here, 180 degrees, between this trigonal planar structure that we have here, it's 120 degrees. For tetrahedrals here, it's 109.5 degrees. So this is, let me see here. Let's do this. So here, this is a tetrahedral here where this bond angle here is the 109.5, and this one here is 109.5, and this is 109.5. And any way I turn it, all of these angles here are 109.5 degrees. Then we have 8 regions for octahedral. Let me see if we have, yeah, so here's an example of an octahedral here, right, where we see 90-degree angles wherever. There's 90-degree angles here, but there's also 90-degree angles here. So for an octahedral, we're just going to see those 90-degree angles. So something that's linear. This is electron deficient for boron, so it is okay to have a trigonal planar here. This is also a very flat molecule. I don't believe I have, I think there's a model structure I can use online to explain. But we have tetrahedral, trigonal biparameter, and then octahedrals here. Noticing these are hypervalent atoms here that can have more than 8 electrons. So this here, let's see if I can. This is one that I believe is much better. All right. There's what we call electron geometries, and then what we call molecular geometries. So here, this is the electron geometry here. This would represent the molecular geometry. What's the difference between this structure and this structure? Yeah, you don't see the electrons. So for molecular geometries, we're not looking at the electrons. For electron geometry, we need to consider the electrons. So here, this creates a cloud of electron density. This creates a cloud of electron density. This is what we're going to consider tetrahedral, while this is considered bent. This is our molecular geometry, and this is our electron geometry, right? So the electron geometry takes into consideration the space occupied by lone pair electrons. So here, this looks like I'm not going to write in the dashes and wedges what we get. When you see these here, these are what we call dashes and wedges. And then we see these straight lines here. This means it's an atom going away from you. This means towards you. And this means in the plane So when we're looking at atoms, why we see these dashes and wedges is very simple, is if you're looking at this structure here, this atom here is kind of going towards you. So we would use a darkened wedge. And this one here is kind of going away from you, so we would use a dashed wedge. If this is the plane of the paper, if I hold it this way, we're good? If I turn it this way, this is now the plane of the paper. If I turn it this way, this is the plane of the paper. So these two are going to use straight lines because, well, it's not going towards you, it's not going away from you, is that these two atoms lie in the same plane. So here, same plane, away from you, towards you. But here, this is what we're going to consider to be the molecular geometry here is going to be bent. But when we're taking the electron geometry, we have to consider the electrons in electron geometry, and it does hold this area here. So you need to know all of this by exam 2. Okay, this has to be memorized. Okay, the shapes of these trigonal planar as well as these bond angles. You have to know the bond angles for anything that's bent, trigonal pyramid. This means less than 109. This means a lot less than 109. Yes?
What figure number is it?
What was that?
What figure number is it?
This is figure number 4.19. We're going to take a look at these two here. Trigonal, pyramidal, and bent. So this, let's see, tetrahedral. So let's do so I just kind of put a bond. This isn't a bond, but I just kind of wanted to designate that this takes up that fourth spot. So here, as far as electron geometry goes, with counting the space for the electrons, that it does take up a tetrahedral electron geometry. Now, for molecular geometry, I'm not gonna erase these just yet, but I will erase them. Is that this only has one set of electrons, one lone pair here. So this lone pair creates an area of density. So it has a slight push on these. These are 109 degrees, but, and let me put, let's put something here. Let me go with this one instead. Tetrahedral, these are all 109 degrees. But as soon as we get this electron pairing here, it starts to push down on these just slightly. So these end up being a little bit less than 109 degrees. But then when we take a look at water, water has two lone pairs. These two lone pairs push more than the one lone pair. So this is why this is much less than 109 degrees. It's because there's simply more electron density because we have those two lone pairs there. So we see that happens here. So here, again, electron density. Once we start getting lone pairs and how many lone pairs there are, we can then start to describe what these look like, right? So once we see the lone pair here, we see something that's kind of a seahorse, and what we consider T-shaped. Let me see if we can. There is a video in here. Oh wait, before we move on, some terms. What we mean by equatorial and axial lone pair electrons. So These here are at the top of the bottom. So if we think of a globe, there's an axis on the top and an axis on the bottom. These are what we call axes, lone pairs. And these are what we call equatorial here. The reason that it might not look equatorial, but if I have a pair of electrons, if I remove this and I remove this, and I put in, do I have another one? Yes, I do. If I put these in here, it still resembles the octahedral shape for electron geometry, because these two densities here of electrons are taking up those two spots there. Okay? If I remove them and I have two lone pairs, the molecular geometry for two lone pairs that come from an octahedral, two lone pairs coming from an octahedral, we have different shapes here. T shape, do we have this T shape here? 1, 2, here. Where is it at? And I have this in the wrong spot. Octahedral. Oh, I think, is it right? Square planar. There it is. I had it in the wrong spot. So here we see the square planar here. So if I put the electron densities here, we have one up here, one down here. This is what we consider square planar for molecular geometry, because it resembles this right here. Two lone pairs, they're on the equatorial, the axes right here, and then these are what we consider equatorial because they're in the middle. So if I were to move these around, shuffle these around, is that now they're in the equatorial position here, these lone pair of electrons that we see there. So we can just simply move those around, but this is going to be a useful chart because you do need to know those shapes that we have there. I just want to show you the take a look at it better. Oh, maybe this is it here. No, not this one here. Better simulation. Okay. These are what we call dipole moments. I'm going to have to finish this in the next lecture. Almost done with Unit 4. But we do need to talk about dipole moments here when I add electronegativity. So this is our dipole moment here, is that we have polarity because the electrons are being pulled, and our dipole moment is right here. But these elements can change, and we'll get more into this, but if I change the electronegativity, we can see how that dipole moment changes. If this becomes more electronegative, that dipole moment is pulled down. But we'll definitely get into this before we start Chapter 5 next week. Exam tomorrow. Other than that, we'll see everybody tomorrow. Pen, pencil, calculator, no Scantron.